Imagine you have a number box called A. Inside this box are its prime ingredients. Now suppose A equals 6. The prime ingredients of 6 are 2 and 3. Now square the number. That means we multiply the box by itself, 6 times 6. So the prime ingredients also get repeated, 2, 3, 2, and 3. In other words, 36 has prime factors 2 squared times 3 squared. Now here's the question. If we find a prime number inside the squared number, must that same prime number have already been inside the original number? For example, 3 divides 36. Did 3 divide the original number 6? Yes, it did. The prime 3 did not appear from nowhere. It came from the original number. This is the idea behind today's theorem. This theorem is like a small key that opens a big proof later. Now let us understand the theorem clearly. Let p be a prime number. If p divides a squared, then p divides a. In simple words, if a prime number is a factor of a squared number, then that prime number must also be a factor of the original number. Let us test this with an example. Take p equals 3 and a equals 12. Then a squared is 12 squared, which is 144. Does 3 divide 144? Yes, because 144 divided by 3 is 48. So the theorem says 3 must also divide 12. And yes, 12 divided by 3 is 4. So it works. But now comes a very important warning. The divisor must be prime. Let us see what goes wrong if the divisor is not prime. Take d equals 4 and a equals 6. Now a squared is 36. Does 4 divide 36? Yes, because 36 divided by 4 is 9. But does 4 divide the original number, 6? No, 6 divided by 4 is not a whole number. So the statement fails when the divisor is composite. This is why the theorem says prime p, not just any number. This theorem is not saying that every divisor of a squared divides a. It is saying that every prime divisor of a squared divides a. Now let us prove the theorem using the fundamental theorem of arithmetic. Think of a as a number built from prime blocks. By the fundamental theorem of arithmetic, every positive integer greater than 1 has a unique prime factorization. So we can write a as a product of primes. For example, maybe a has prime factors p1, p2, p3, and so on. Now square a. Squaring means multiplying a by itself, so a squared equals a times a. That means every prime factor in a appears twice in a squared. If a had prime blocks 2, 3, and 5, then a squared has 2, 3, 5, and again 2, 3, 5. So the prime factors of a squared are not new primes. They are the same prime factors of a, just repeated. Now suppose a prime number p divides a squared. If p divides a squared, then p must be one of the prime factors in the unique prime factorization of a squared. But the prime factors of a squared are just the prime factors of a repeated twice, so p must already be one of the prime factors of a. Therefore, p divides a. That completes the proof. Let us make this concrete with a number. Take a equals 20. The prime factorization of 20 is 2 squared times 5. Now a squared is 20 squared, which is 400. The prime factorization of 400 is 2 to the power 4 times 5 squared. Notice what happened. The primes are still only 2 and 5. Their powers doubled, but no new prime appeared. So if someone says a prime p divides 400, then p can only be 2 or 5, and both 2 and 5 also divide 20. That is exactly what the theorem says. When we square a number, prime powers double, but the prime names do not change. New prime factors do not suddenly appear. In future proofs, we may know that a prime divides a squared number. This theorem allows us to immediately move backward and say, then that prime also divides the original number. Let us summarize. Today you learned the prime inheritance rule. If p is a prime number and p divides a squared, then p divides a. You also learned why the word prime is essential. Composite divisors do not always follow this rule. For example, 4 divides 36, but 4 does not divide 6. Finally, you learned the proof idea using the fundamental theorem of arithmetic. A number has a unique prime factorization. When we square a number, the same prime factors simply repeat. So if a prime appears in a squared, it must have come from a itself. Squares repeat prime factors. They do not create new prime factors.